All right, so we have been talking about this coping with NP completeness. How do you try to solve hard problems? And we went through branch and bound and backtracking, which was a way to find the optimal solution and sort of try to improve performance, but still we're getting exponential time. Now we're looking at approximation algorithms where the algorithm runs in polynomial time, does not find the optimal solution, but has a guarantee that the solution it finds is not too far from optimal. In particular, we have for a minimization problem, it always finds a solution that's no more than alpha A times the optimal solution. Right? And so what I'm going to do now is give you a couple examples of approximation algorithms just to show you how they work. And the first two are going to be variants of the traveling salesman problem. So let's look at TSP with triangle inequality to start. We talked about this before, but it's just the TSP problem, traveling salesman problem. So you have a complete graph with edge lengths, and your goal is to find the shortest tour that visits each vertex exactly once. If the edge lengths satisfy the triangle inequality, that just says that if I pick any three vertices, U, V, and W, U, V, W, then going from U directly to W, that edge length has to be shorter or no longer than the edge going from U to V and then V to W. So it's kind of saying the direct path has to be shorter than the one that goes through an intermediate vertex. If that's satisfied for all, sets of three vertices in the graph, then we say the graph satisfies the triangle inequality. So certainly like Euclidean distance satisfies the triangle inequality, right? I mean, most kind of distance measures do, but there are lots of graphs if you get it from some other process that wouldn't satisfy triangle inequality. Okay, and I guess I actually meant to draw that picture, down here. But you get the idea, right? So this, I guess, is the length from U to V. This is the length from V to W. And this is the length directly from U to W. Okay, so how do we try and compute approximation, or what would be an idea for an approximation algorithm for the minimums or for the traveling salesman problem? I'm going to give you an algorithm. It's not too difficult to follow. We've built up all the pieces for it, and then we'll try and analyze what's its runtime and what's the approximation factor that it gets. So the algorithm operates as follows, and I'll draw some pictures just to show you. We're given this graph, a complete graph, compute the minimum spanning tree of it. Then double each edge. So it's actually not a graph in our technical sense, it's a multi-graph, like when we went back to the bridges of Königsberg problem, right? You have multiple edges between the same pair of vertices. On that graph, now that you've doubled every edge, every vertex in that graph has even degree. Do you agree? Because if it had odd degree before, we doubled all the edges incident with that vertex, and now anything times 2 is an even number. So we now have, yeah. Create another, yeah. Duplicate, yeah. Maybe I should say duplicate the edge. And now I have a graph, right, in which every vertex has even degree, and I can compute an Eulerian cycle on that graph, right? A tour that traverses each edge exactly once. Then start going along that tour. That tour visits vertices multiple times. Go along. Each time I hit a vertex, record it. But if I go back to a vertex I've already visited, then just skip it and go immediately to the next one. And because of the triangle inequality, this skipping is always a shortcut. Because basically, rather than going down to some vertex and across, I'm just going to go directly to, take the kind of hypotenuse almost, right? The direct edge on the triangle. And so let me draw you some pictures to illustrate this idea, and I think it'll become clear. But basically that last thing, shortcut the tour, shortcut the Eulerian cycle to turn it into a tour. After that, we've got a tour, and that's going to be the output of my algorithm. So here, I'll say duplicate. And let me draw an example. So step one was, let me draw a simple graph. In this example, it's just going to be a Euclidean graph. So I won't draw all the edges, and then the edges will just be given by the distance on the page. So let's say I have something like this. Okay. And then I'm going to copy this cloud and paste it a few times. There, and there. Okay. That way I just have my same set of dots to show the different pieces of the procedure. So step one is going to be compute minimum spanning tree. Okay, so I just successively add the shortest edge that doesn't create a cycle, right? So it might be this edge, then I don't know. Often in these like Euclidean ones, it's a little hard to even decide what are the shortest edges, but there's a lot of like ties. But let's say that's my minimum spanning tree. So now step two is double each edge. Duplicate each edge. So now I have what I had before, this minimum spanning tree. And then I create a second edge. I'll draw them kind of curvy just so that they look different. Okay, and now you see in that new graph, like in this original graph, some vertices had odd degree. Like actually, all the vertices except for one had odd degree. But now once I double, all the vertices have even degree. Top one has 2, the one right here has degree 6, 2, 4, and 2. So an Eulerian cycle exists in this graph. So now we compute it. And it's just going to be a traversal of all the edges. We could use Fleury's algorithm, if you remember. It's just like go across an edge and delete the edge. And if you have a choice between edges, always go across the edge that doesn't disconnect the graph. Unless you can't, in which case just go across any edge. So once we get to that, we get an Eulerian cycle. It's going to look something like this. Let's say we go out on this. Then we come back, go out here, come back, down to here, down to there. And now, so that's 3. And now I just march along that and shortcut anytime I'm going to visit a vertex a second time, right? Just to skip all but the first appearance of each vertex. So maybe I'll draw it. Well, how about I draw it over here? So let's say I go up like this, right? Now my next edge should come back, but that visits the same vertex. So I shortcut and go straight across. Straight across. The next one, again, actually should go back. If you see, right, it goes back to here. So I shortcut and go down to the next one. Then it goes out to here. And then I should come back like this, right? Using this edge here, but that again visits the same one. So instead I shortcut and go to here. Right, and each one of these shortcuts, like I can draw it over here, is actually a shortcut. And that then is my final tour, the red thing. So for shortcut to create the tour. Does the procedure make sense, the 4 steps? Any questions just on how it operates or? Okay, so now we have 2 pieces, right? One is for this to be an approximation algorithm, it should have polynomial runtime, which I think you agree it does. It requires the computation of a minimum spanning tree and the computation of an Eulerian cycle, both of which we said can be solved efficiently. But let's just write out the runtime. And then we need to try and figure out the approximation factor of it. And the key thing for that, if you already are convinced on the runtime, think about this for a second, is how can I try and relate the length of the minimum spanning tree to the length of the optimal TSP tour? That's going to be the key to us figuring out how long that red tour can be relative to optimal. I think in this case, actually, it found the optimal, but that was like by luck, kind of, right? I mean, it was just, if I'd done the Eulerian tour in a different way, I think even in the notes, I did it slightly differently, or maybe I laid out the points a bit differently, and it's not optimal for the one I drew in the notes. So, okay, sorry. Actually, we're going to do approximation ratio first. I thought we were doing runtime first, but I'm wrong. So can anyone think, like, what can I say about the TSP tour length relative to the minimum spanning tree length, like the sum of all edges on the minimum spanning tree? Can I relate those 2 quantities? Yeah. You said TSP is shorter than the minimum spanning tree? Other way around, minimum spanning tree shorter than TSP. Do you have an argument for it or just kind of intuition? You're right. I was just wondering if you knew or if you had a supporting argument. We kind of did, actually. Yeah, not quite, but we said basically that path, right, was a candidate for the minimum spanning tree. So the minimum spanning tree must be shorter than that shortest path that went through those vertices, right? Kind of same argument, but does someone else have like maybe precise ones? So it's, yeah. Yeah. That was exactly right. Yeah. So what was said there was the TSP tour, if I delete an edge from it, pick any edge, that creates a spanning tree, right? I mean, the tour has a cycle, so it's not a tree, right? But delete one edge, now I have a spanning tree. The minimum spanning tree by definition has to be shorter than or equal to in length of that, or that one, the one that you obtain by deleting an edge off the TSP. Since all the edge lengths are non-negative, right? That's the input. That means the TSP has to be longer or greater than or equal to the minimum spanning tree. Okay, perfect. So consider the TSP tour optimal, like the true optimal. Delete an edge. This is a spanning tree. Must be at least as long as the minimum spanning tree. And so I get the length of optimal TSP has to be greater than or equal to the length of the MST. Now, with that, we're almost there actually, because let's look at the next steps. We double each edge in the minimum spanning tree, right? We duplicate each edge. So now all the edges in figure 2 there have to be no more than 2 times the optimal TSP, right? Because we copied each one. So that means the length of the Eulerian cycle, which traverses each edge exactly once, is no more than 2 times the length of the optimal TSP. Here, all we did was shortcut, right? And by the triangle inequality, we shrunk the tour. We can't have made it any longer. Thus, our final tour is no more than 2 times the length of the optimal. So this is a minimum spanning, or sorry, this is an approximation algorithm with a 2-factor approximation. So let me just write that out. Length of Eulerian cycle equals 2 times length of MST, which is less than or equal to 2 times the length of the optimal TSP. And then shortcutting can't increase length. By the triangle inequality. Therefore, length of tour is less than or equal to 2 times opt. Which implies the approximation ratio is 2. Which is actually really good for such a simple algorithm. Runtime. Basically, my operations are compute a minimum spanning tree and then compute an Eulerian cycle. And then do shortcutting, but shortcutting is just march through the order of the vertices in the Eulerian cycle and delete all but the first entry, right? The first occurrence of each vertex. So it's just, that last part is just linear in the length of the Eulerian cycle, which is 2 times the length of or 2 times the number of vertices. So that part's linear time. Computing an Eulerian cycle is n² time if you use that Fleury's algorithm that I gave you, that one from the 1800s, but there's a better algorithm that runs in linear time. And so the bottleneck is going to be computing the minimum spanning tree, which in our case here, right, the TSP instance is a complete graph. So it has v² edges in it. And so the runtime for minimum spanning tree is going to be v². And so this overall algorithm runs in v² time. So let me just sketch that out, the argument I just made. MST is order v² time. with Prim's algorithm and an array for the priority queue, right? This is actually kind of fits in. If you remember back on the midterm, there was this question, right? That like, if you have a graph with order v squared edges, is it better to implement your priority queue as an array or as a min binary heap? And it's actually better to do it as an array in this case. Same with Prim's algorithm, which really looked like Dijkstra's, right? So here, the best way to get the best runtime, you should use just an array because the graph is so dense. So Prim's algorithm and an array for, the priority queue. Eulerian cycle is big O V with the best algorithm, or V squared with Fleury's algorithm. Either works. It doesn't dominate the MST time. And shortcut is big O V time. So our overall runtime is big O V squared. There's actually another algorithm for the TSP, an approximation algorithm that gets it down to 3 halves for the approximation factor rather than 2. It instead runs in V cubed time instead of V squared time. It's called the Christofides algorithm. And the idea is very cool. I'll just tell you very briefly. This is like a total aside, but if you think about what the key idea was, so 1, it was compute the minimum spanning tree. And then 2, it was find an Eulerian walk or cycle on that. And so to do that, I had to turn the odd degree vertices into even degree ones, right? So that an Eulerian cycle existed. The way to do that in this simple one was just double each edge. And then I created every vertex was even degree. But some of them were already even degree, right? Some are even and some are odd. And so the Christofides algorithm, instead what it does is it finds the odd vertices, the ones that have odd degree, after computing the minimum spanning tree. And it's a property you can establish that there's an even number of those. And then all I have to do is pair them up, right? Add an edge between, like if I have 4 of them, create 2 pairs, right? By drawing 2 edges between them. And that will be 1 more edge incident on each odd vertex, and that will make them even. And you can show that those edges that you add cost no more than half the TSP. So you get one length of TSP to do the MST, right? Because we said the MST is no more than the TSP. And then you get another half only from pairing up odd degree vertices. And so it's the kind of same procedure, but it's a little bit more complicated. And this pairing up odd vertices in the cheapest way becomes the bottleneck in the computation rather than minimum spanning tree. But it's kind of cool algorithm. It's from the 70s. And for like a very long time, it was the best known approximation algorithm for TSP with triangle inequality. More recently, there's been some papers that have very slightly reduced this 3 halves to something a bit smaller, but they're quite complicated, not so practically relevant. Now, the whole idea hinged on this idea of shortcutting, right? Which is why we needed triangle inequality. To turn it into an actual tour that visits each vertex exactly once, we had to shortcut. If we don't have triangle inequality, this whole thing doesn't work. Because now when we try and do shortcutting, we could be all of a sudden using super long edges in our so-called shortcut and ruining all our guarantees. And so the general TSP without triangle inequality is a different story. And we can actually come up with a really nice negative result for this one, which says, let's suppose we had an approximation algorithm for the general TSP. I'm going to use it to solve Hamiltonian cycle. What that then means, since Hamiltonian cycle is NP complete, it basically means that unless P equals NP, no constant factor approximation exists for the general TSP. So let me show you how this works, right? So we're supposing we had an approximation algorithm for the general TSP. It gives us an alpha approximation. And I'm given an instance of Hamiltonian cycle, and I'm going to convert it into a TSP instance and use my approximation algorithm to solve it. So what do? So I'm given this instance. I create a TSP instance. So I'm given this, right? And I create a TSP instance with the same vertex set, with the complete set of edges, and with edge lengths defined as follows. It's kind of like what we did before when we reduced Hamiltonian cycle to TSP, but now I'm going to try and reduce it to this approximation algorithm. So I'm going to make on an edge UV, I make the edge length 1 if UV is in the Hamiltonian cycle input, right? E is part of the Hamiltonian cycle input. And I make it really long otherwise. And how long I make it is related to the approximation factor. So I make it n times alpha A. That's the approximation factor of this supposed algorithm, plus 1. If it's not an edge in the Hamiltonian cycle instance. Now I run my approximation algorithm, my alpha A approximation algorithm on this instance I created. Yeah. This thing? Yeah. Well, that's meant to be this A right here. It's the approximation for this algorithm A. So, yeah. My font's a little bad, I guess. So let's say if I run this algorithm, right? There's two options. One, it happens to use all edges of length 1, right? Then it found a Hamiltonian cycle. Option 2 is it doesn't use all edges of length 1. And then we'll figure that case out next. So when A is run on this graph I just created, there's two options. Option 1, it uses all edges of length 1. Therefore, it found a Hamiltonian cycle in G. So if it happens to find a tour with all length 1 edges, then we found a Hamiltonian cycle. And if it didn't, if it outputs something larger, the cost is going to be so large that even dividing by the approximation factor, I now know that the optimal has to be bigger than n, which means that even the optimal solution couldn't be a Hamiltonian, couldn't use all edges of length 1. So let me try and convince you that. So case 2 is it uses at least one edge of length n, I have trouble drawing an alpha A plus 1. Then the tour it finds has a length greater than or equal to n minus 1 edges of length 1 plus 1 edge of length n alpha A plus 1, right? It maybe used n minus 1 short edges, and it used at least one long edge. So it has to cost at least that much, which if I just combine those two, I get n alpha A plus n. Right, the minus 1 cancels out the plus 1. This minus 1 here cancels out this plus 1, and so I get n, and then I get another alpha A n's. So I get n plus 1, or I get n alpha plus n. Now, since A is an alpha A approximation, we know that the opt has to be less than or equal to the length of this tour that we found over alpha A. Right? By the definition of an alpha approximation, it always outputs a tour that's no more than alpha A times the optimal. So I'm just arranging it, right? We know that the optimal then has to be no more, or sorry, we know that the I have the, that's why probably you're wondering what I'm doing. That's wrong. The optimal has to be at least the cost of the tour that I found divided by the approximation factor. Right, this is, I guess, since by the definition of approximation factor, we have this. If you just go back to that slide. I just rearranged it. Opt I is greater than or equal to AI, which was the cost we got, over the approximation factor. And if we look at this term, right, we get n plus n over alpha A. So it's some number that's strictly bigger than n. So I don't want to have an inequality. I want to have a strict inequality. Strictly greater than n, which implies that the optimal tour on that graph I created can't use only length 1 edges, which means there is no Hamiltonian cycle. So my approximation algorithm either outputs a tour of length n, in which case we found a Hamiltonian cycle, or it outputs a tour that's so long, because it used one of my super long edges, that I know that even the optimal would have to be bigger than n, meaning that there is no Hamiltonian cycle in that graph. So I've just used my supposed approximation algorithm to solve Hamiltonian cycle. And so the result then is this. Unless P equals NP, there's no K-factor approximation for the general TSP, the one without triangle inequality, unless for any K greater than or equal to 1. So it's what we would call inapproximable. Which is kind of cool. I mean, like we're seeing that there's these problems that have they're not that different. Like TSP with triangle inequality, we also said is an NP hard problem or NP complete in its decision version. But we can approximate it to factor of 2 in V squared time, or a factor of 3/2 in V cubed time. But now if I drop the triangle inequality thing, still it's just a problem that's NP hard, or its search version is NP complete. But now we can't approximate it at all. And the last example I want to give you is revisiting an old friend, Knapsack, without repetition. And we're going to give an arbitrarily good approximation algorithm for it. But why don't we take a 5-minute break, and then we'll come back to that one. Okay, so last example is going to be knapsack without repetition. If you remember, for this problem, right, you're given a set of items. They each have a weight and they have a value, and you have a budget of weight, capital W, right? And you want to pack your knapsack with a set of items that doesn't exceed your weight capacity and has maximum value. We gave a big O n times W time dynamic programming algorithm for this. We talked about how that wasn't polynomial time because it scales, the runtime scales with W, right? Which is the value of one of the input numbers. It only takes m bits to represent, like with m bits, I can represent a number as big as 2 to the power of m. And so this could run, this one up here could run for a very long time, right? Like take a 100-bit number, I can represent a W of 2 to the power of 100. And my for loop in there ran all the way from 1 up to then 2 to the power of 100. So it would run forever, basically. But we can now kind of create a modified approximation algorithm that will come very close to optimally solving the knapsack without repetition. For it, I first have to give you, very quickly, I'll give you an alternate dynamic programming algorithm. So I'm going to give you one that runs in big O NV time instead of big O NW time, where V is the sum of the values in the input instance. It'll just be more useful for coming up with the approximation algorithm. And then I'm going to modify it to create my approximation algorithm. So let's quickly go through the approximation, or sorry, the big O NV dynamic programming method. So we have n values, or n items. They have values v1 through vn. And we let capital V be the sum of all those values. They have weights w1 through wn, and you have a knapsack capacity of w, and we know the goal. So my definition of the subproblem for dynamic programming is a little bit unusual maybe, but this is why I didn't present it earlier. I'm going to let k, v, j. It looks a lot like what we did before, right? We had a 2-index subproblem before when we got the NW, where we limited the number of items and we limited the capacity of the knapsack to some smaller W. So now instead KVJ, and then before with K, we recorded the best value I could obtain using items only 1 through J and a knapsack of capacity like some small lowercase w. Here instead, K is going to record the least weight I can use. To achieve a value of V using only items from 1 to J. So it's what's the lightest knapsack I can create that gets me exactly a value of V and uses only items 1 through J. It might not even be possible, right? Like there might not be a combination of items that gets me exactly a value of V, in which case I make this weight infinity. So K V J equals infinity if no such set of items exists. Now my ordering of subproblems or my recursion looks very similar to what we had before, where I just consider, let's suppose I add in one more item into consideration, item j plus 1, and I want to update my best solution. So let's write vj plus 1 recursively. there's two options, right? Just as before. Either I don't use item j plus 1 in my minimum weight solution for this problem, in which case it's just going to be Vj, Kvj, or I do use it, in which case I have this subproblem, which is what's the minimum weight. I can get the remaining value, so the value minus the new item j plus 1, using items 1 through j, plus the weight of that new item, j plus 1. Right, this subproblem here is like, what's the minimum weight I can use to achieve a value of v minus vj plus 1, and then this is the weight of item j plus 1, which gets me that value vj plus 1. So in total, the combo of those two will get me the correct exact value v. And that's it, right? I have the two options. I don't use item j plus 1, or I do. Okay, smallest subproblems. Oops. K0j. So what's the lightest backpack I can use to achieve a value of 0? It's just going to be 0. And the other one is I have a value I want to achieve, but I don't have any items. Right, so what's the least weight I can use to achieve a value of 10 with no items? That's one of the infinity ones, right? Like there's no solution to it. So it falls into no such subset up here, right? No such subset of items exists. So I initialize these ones to infinity. So for all v equals 0, 1, up to capital V. And now for runtime, I just fill in this table, right? It goes for j from 1 to n, and for lowercase v from 1 or 0 up to capital V. And each entry gets filled in constant time, right? Because it's just taking a minimum of 2 previous entries in my table. So we do for loop over v equals 0, 1 up to v, and j equals 0, 1 up to n. So the runtime is what we are searching for, big O N V. And then the last question, maybe just to ask you, is, okay, I filled in this huge table. What's the answer now to the knapsack problem? Because the table's kind of weird, right? It's recording weights. Right, an entry says, what's the lightest knapsack I can use to create a value of V using only items 1 through J? Yeah. Somehow I have to check against my budget weight, right? Capital W. Any other ideas? Yeah. Okay, but the first non-infinity one still might weigh more than my capital W, right? Which is my budget on the weight. But Yeah. Exactly. Yeah. Start at the maximum V and just iterate down until you hit one with a weight underneath the budget. So final answer is max V such that KVN, right? I only have to consider using all the items, is less than or equal to my capital W. So now I'm going to use this to design an approximation algorithm. And what I do, I have to make sure for my algorithm to run efficiently, I have to make sure capital V isn't too big. So all I'm going to do is scale all my values and my weights. Or actually, I'm not even going to touch my weights because this algorithm doesn't scale badly with weights, right? It scales with values. So I'm going to scale down my values so they're not so large. And so first, I mean, this is just like a pre-processing step. Discard any item that weighs more than my budget because I can't use it anyway. Then find my maximum weight, Vmax. And then rescale all the values in the following kind of weird looking way. The new value is the old value divided by Vmax. I mean, maybe it's better to read it like that. Vi divided by Vmax times n over epsilon. And I take the floor, so it's an integer. We'll figure out why I'm doing exactly this. It's not totally clear. But basically now, if you think, right, each Vi is smaller than Vmax or less than or equal to Vmax, so that my new values are at most n over epsilon. So I've bounded like the maximum possible value I'm willing to tolerate is going to be n over epsilon, where epsilon's like a design parameter here that I'm going to use. Now I just run my big O NV approximation algorithm or dynamic programming algorithm on these like scaled weight problem and output the solution. And the claim is this, which is kind of neat. So this algorithm is a 1 minus epsilon approximation algorithm with a runtime of n cubed over epsilon. So if I fix any epsilon, let's take 0.01, I'm guaranteed to get a solution that's within 99% of optimal, right? It's a maximization problem. So now my approximation factor is always less than 1. But I'm going to guarantee to get a solution that's at least 99% of the optimal. And my runtime will be n cubed divided by a constant, but that constant is 0.01. So it's like 100 n cubed. It's still polynomial time, right? But as I make my epsilon get smaller and smaller, like suppose I make epsilon 10 to the minus 5, then my runtime is going to be 10 to the 5 times n cubed. So for any finite epsilon, this is a polynomial time algorithm. It doesn't violate NP completeness or anything, because if I actually let epsilon go to 0, the runtime goes to infinity because epsilon's in the denominator. But it's basically a method to get an arbitrarily good approximation in polynomial time. So first, let's do the runtime, then we'll do the approximation factor. It's actually pretty easy to do both, and you'll see why we picked that very specific scaling. So first of all, the runtime. I already said this, each Vi hat is less than or equal to n over epsilon, since Vi is less than or equal to Vmax. So in my scaled problem, the sum of all my values is less than or equal to, just plug in that upper bound of n over epsilon. And I get sum from I equals 1 to n of n over epsilon, which equals just n squared over epsilon. And so my dynamic programming algorithm, which runs in n times v time, will be n times n squared over epsilon. It's just going to be n cubed over epsilon. So runtime is pretty easy to see. Approximation factor, it's not hard, but it takes just a little bit more to think about. So what we're going to have to do is compare the solution to the original problem, the one where I haven't yet scaled the weights, to the solution I get from this scaled problem. And so the comparison takes a few steps. What we're going to do, so let's suppose that this optimal solution of the original problem picks a subset S of items, and it gets a value of K star. The solution that I get, so first of all, I guess, let's look at that optimal solution and sum up the scaled values for it. So the v hats for it. So plug in the value or the expression for v hat. I and S, the v hats are the floor of vi times n over epsilon v max. Oops, floor. The floor makes a number smaller, so if I just drop the floor, then I get it greater than or equal to. So this is greater than or equal to the sum from I in S of vi n over epsilon v max. And then you see right here, that's the sum of the real values in the optimal solution, right? S is the true optimal solution. So this part right here, that is K star. Sorry. I'm doing greater than or equal to. Sorry, what I said is a little bit wonky, right? So this is the floor. I want to make it, the floor is, of course, smaller than what's inside. And it's bigger than what's inside minus 1. Right? The floor of 3.5 is 3. And 3 is bigger than 3.5 minus 1, which is 2.5. So like always subtracting off, the floor can do no more than subtract 1 off. It actually can only subtract like 0.99999 off, right? And, so what I wanted to do is write that minus 1. Replace the floor by its argument minus 1. And it has to be bigger than that. And so now if I write this, this looks like K star times n over epsilon v max minus, I get n ones, or at most n ones, sorry. Right, the minus 1 gets summed up the number of times equal to the number of items in my optimal solution. I don't know how many items are in my optimal solution, so I just say at most all of the items are in it. Right, and then so I get an n there. Okay, so that's step 1. Now let S hat be the items chosen in our optimal solution to the scaled problem. Then we have that if we sum up the items in the scaled problem, that one has a hat on it now. Again, sum up the scaled items. What do you think? Do you agree with this first step I've written? Or can someone explain why did I write that the scaled values, the sum of the scaled values in my optimal scaled solution has to be better than the sum of the scaled values in the optimal solution to the original problem? Is that logic making sense? So for this problem with the scaled V's, that's the best solution. S hat is the best solution. S is not the best solution for the scaled problem. It's the best solution for the original problem, right? So S is a candidate solution for the scaled problem. This one, the hat one, is the best one. So it's got to be better than any candidate. So this is solution this one is solution for unscaled problem. It's not optimal for the scaled problem, right? The first thing is optimal for the scaled problem, the hat one. The S, we don't know if it's optimal for the scaled problem, so it can't do any better. And then I plug in what I have above, right? This second term is now exactly what I wrote over there. I know this argument is, there's nothing like too complicated going on, but I'm trying to keep track of these things, right? To compare the solution I get from my scaled thing to the original, the true optimal solution. So this is this K star n epsilon V max minus n. Finally, the thing I want to know is how well does my scaled solution do on the original values? Right? We know the optimal one, if I put an S here, it gets me K star. But I'm going to output S hat as my solution, right? The solution to the scaled problem. So I want to know what's the sum of the values, the real values with my scaled solution versus the true optimal solution, the true optimal, like where I solved it without scaling. And so this is greater than or equal to sum over the I in S hat of VI hat times epsilon V max over N. What did I do here? I just used the fact that VI hat is less than or equal to VI times N over epsilon V max, right? Because it's the floor of that. Just here, VI hat is this expression. So if I remove the floor, then VI hat is less than or equal to what's inside the floor. Okay, we're almost there. Which is greater than or equal to. Now, if I look, right, this piece is, I already have the answer for it. This piece here is that K star N thing. So I can plug that in. K star N over epsilon V max. Minus N, and that multiplies epsilon V max over N. And if I look, right, this term here exactly cancels out with this term here. I'll just write so I get here, I get a K star minus, and then the second term is going to be epsilon V max. Right, because the ends and cancel out. And then my final argument is that K star has to be at least as big as V max, because I discarded all the items that weighed too much. So I know I can always fit V max in my knapsack. Right, like that's just the single item, and that item weighs less than my budget. So this then has to be, this value is less than or equal to K star. And so I get that this thing is greater than or equal to K star 1 minus epsilon. And that is my final result. And then let me answer your question. Yeah. Yes. 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 Here in this step, because it's on the scaled weights. S is the optimal solution to the unscaled weights. S hat is the optimal solution to the scaled weights. Right? They don't have the same value, right? Just like once I've scaled them, I've changed the problem potentially. That's the whole thing. Like if you didn't think I changed the problem, then I should be able to scale and just get the optimal still. But the whole thing is once I scale it, and now I optimally solve that scaled problem, I no longer know if what I found is the optimal solution to the unscaled problem. Yeah. Yeah, those are the scaled values. Pardon? You're applying the scale on the unscaled. Yes. For V high though, not for VI hat. But that's the crux of the argument. Is maybe a point on here just so that it's easier because it's high up. But so this is the optimal solution for the problem instance that uses the hats. So nothing can get a better value than this on the one with the hats. This is an optimal solution for the one without the hats, but I'm calculating how well it would do on the problem with the hats. So it can't do better than the optimal. Of course, if we didn't have hats here on any, like if we remove these two hats, then the inequality would change directions. Because we know that S does better on the unscaled problem than S hat does. I agree the problem's like the argument's a little bit complicated, and I think it's primarily because I'm like doing all this stuff with hats and not hats and trying to relate everything. But what's very cool in the end is that we're getting an algorithm that runs in polynomial time and gets me a solution that's no more than 1 minus epsilon from the optimal solution. And so It doesn't violate any fundamental properties because, as I said, as epsilon goes to 0, the runtime goes to infinity. So we cannot guarantee that we solve it optimally in polynomial time, but we can get arbitrarily close. And so there's this interesting, what we call an approximation hierarchy. There are problems for which there's no finite approximation. TSP without triangle inequality is an example. There are ones for which there's a finite approximation. TSP with triangle inequality was a good example where we got a 2-factor approximation. And then there are these problems that have an arbitrarily good approximation. This is called a polynomial time approximation scheme. And there are a few of these problems. They're still hard problems, right? Their search version is still NP complete, but that includes Knapsack without repetition. It also includes TSP with Euclidean edge lengths. A special case of the TSP with triangle inequality. But most problems don't have these PTAS algorithms, polynomial time approximation schemes. And that is basically all I wanted to cover. I had just a tiny teaser thing on local search, which just was our third category of algorithms. We've gone through now find the optimal, but still exponential time, which backtracking and branch and bound. Approximation algorithms, which are great, but can be hard to find for arbitrary problems. Like if you're going off to work somewhere and you encounter a hard problem, it's unlikely you're going to be able to derive an approximation factor for it. You might want to know which problems already have good approximation factors, but that's about it. And then there's these just heuristics. And so one is a general paradigm is called local search, which really is what the simplex algorithm was doing, where basically we start with an initial solution, S, and we define a notion of neighborhood for solutions. And we say, well, there is a solution S prime in the neighborhood that has better cost, move to S prime and repeat. That's all local search does. In section 9.3 of the text, there's an example for TSP, where basically the notion of neighborhood is a tour that differs by only 2 edges. So what it gets you to do, it's the picture I think is that describes it all, is let's say that somehow I arrived at this tour. Oops, that's not what I wanted to draw. That tour, then I can undo the cross. Like a tour that differs by only 2 edges is one where I delete those 2 crossing edges and instead I add in these 2. Right, get rid of these crossing ones and add in my red ones. And that would be a neighbor, what's called a 2-opt neighbor of a TSP tour. And so I could repeatedly start off with some initial tour, repeatedly pick pairs of edges, and then try and do this sort of delete those 2 and connect them up in the other way that's feasible and check if I get a better tour. Repeatedly do this. This works fairly well. And there's much more, much fancier algorithms out there, but that's just one example. Okay, so I think that's all I wanted to cover. We didn't get to go over the a brief summary. So let me stop recording, then we can just quickly chat.